What have we done so far? We started machine translation, and in particular, neural machine translation. We said how we are gonna, what is a machine translation task, how we are gonna model it, how we are gonna train the model, what is the loss function, and how we are gonna evaluate it using the blue score. We learned about GRUs and we learned about attention mechanism a little bit. And then we said maybe a good idea is to reverse the order of the words. So that's an idea. You take it to the computer, and yes, you see that it's working. Reversing the order of your input sequence is helping. So these two are the things that we did last session. And another thing that we did last session was that we had this baseline translator which had nothing to do with deep learning. And then we were using a neural network to rescore the outcome or the recommendations from the statistical machine translation. And after rescoring, we were getting better translations. So we were using neural networks to complement the results of a statistical machine translation. This paper is going to be along the same lines. We are going to use neural networks to help a statistical machine translation, but in a different way. And we're going to see how. But first, a quick recap of the encoder-decoder architecture. So a sentence goes in, a sequence of words, actually a sequence of word vectors. Then we know what this formula is. This is just a GRU. It's a gated recurrent unit. There is some new information going in H tilde. And now J, these are not vectors. So J is the jth entry of your vector. And now tan H, you can see that it's acting element-wise. So a new information goes in, you embed it, you multiply it by a matrix, you have another matrix, you reset some of the information from the previous hidden state, and then you update some of it using this. So there's a reset gate, there is an update gate. Then you take that sentence, you push it through your recurrent neural network, and in the end, you're gonna end up with a single vector. So we are not doing attention anymore. It's just a sequence modeling. So you're gonna have C. For the decoder, you have an output sentence and you're outputting it one after another. So you first output the first word, the second word, up until the nth word. What you're gonna do is you're gonna take this C and initialize H0 or H prime 0. Prime is for the hidden state of the decoder. Previously, we were calling it S. You can call it H prime. Again, this is going to be a gated recurrent unit. Some new information comes in. So we just outputted this word. We're going to take that and embed it, multiply it by a matrix, and then reset some of the information from the past. This is the update gate. This is the reset gate for the decoder. And then in the end, you're going to need to output the probability of the next word in your translation. So what is the probability of the next word? Because these are one-hot vectors, the question is what is the probability of the jth entry of the outputted vector being a 1 and the rest of them being 0. You model that by a bunch of matrix vector multiplication. So this is your softmax. And then the question is what is G? If you put a matrix, it's going to have a huge dimension. The dimension is going to go to the dimension of your vocabulary, to the size of your vocabulary. And the input dimension is going to be also big because you're having a big dimension for your hidden states. And then if you multiply, if you have a output matrix, a single output matrix, it's going to be a huge matrix. And it's not efficient in terms of parameters and in terms of computation. So what you can do, you can decompose G and then first go to a lower dimension. And then from the lower dimension, you go to the size of your vocabulary. And this way you're saving some dimensions, some computations. So you're gonna decompose G as GL, GR, left, right. GL, GR is gonna take you from dimension 1000, this is the dimension of S, to a lower dimension, let's say 500. And then GR is going to take you from dimension 500 to the size of your vocabulary. And this we saw before. This is the max out activation. So you're maxing out. If somebody gives you a vector, you take pairs of elements in your vector and then just output the maximum of those two numbers. So that's a max out activation, and it's a nonlinear activation. It's going to help you regularize your network, the output of your network, actually. And then what is S? The question is, what is S? It depends on the hidden state of the decoder, the previous word, and the context of your encoder. So that's your encoder decoder architecture. And this we saw before. This is just a new notation. We saw everything that I mentioned here before, except for how you're decomposing your matrix and how you're saving computation. So far, so good. How are we going to use this? We know that a pure neural network at that time was not powerful enough to give you good translations on its own. So we are going to use the help of a neural network to increase the performance of a classical statistical machine translation. So what is a machine translation? In general, somebody gives you an English sentence and you want to know the probability of a French translation. You can write down the Bayes rule. This is going to be, the Bayes rule is just going to help you reverse the order of the conditioning. So now you have P of E, condition on F. Then you're going to have a language model. The language model is going to give you the probability of every single sentence in your language. How probable is this sentence? And then you have a translation model. And then you are dividing this. This is proportional. So you have to normalize it by P of E. So there is a division here that I'm not showing, and it's hidden inside this proportion. If you take log from both sides, here you're gonna have, this is the joint distribution. P of E given F times P of F is the joint distribution. It's gonna be P of E comma F. So that's the joint distribution. And your joint distribution, you're gonna model it. In a statistical machine translation, you're gonna model it in terms of a bunch of features that you hand engineer. It's gonna take an input, an output translation, and an input sentence. It's gonna featureize it, and then it's going to be a linear combination of those features. And we don't care how you featureize it. Maybe it's a bag of words. Maybe you're creating the co-occurrence matrix, and then you're doing matrix factorization on that. Whatever that you do, you're going to end up with a bunch of features. So that's the term in the numerator. The denominator, you're dividing by P of E, or you can actually call it Z of E. So you're dividing by something, and that's going to give you the log of that something. So you have two terms. The question is, how are we going to use a neural network to help you? We are going to use whatever that we learned here about a recurrent neural network encoder decoder. We are going to end up with a probability, and we are going to use that probability that is heavily parameterized by the parameters of our neural network to score pairs of input-output sentences. Okay, it's going to give you a bunch of numbers, and those numbers you're going to add as features to your dictionary of features. Some of them are coming from classical machine learning. Some of them are coming from your neural network. By the way, this is trained. These zetas are already optimized, and the training process is you have a likelihood for your neural network and you're training it. It's independent. Once the training is done, you're going to end up with a bunch of features coming out of your neural network. You're adding them to whatever hand engineer features that you had in your statistical machine translation, and then you're going to translate. You're going to train these parameters, WNs. So it's going to be a simple linear regression. So one might say, are you actually adding features that are independent from what is already in your statistical machine translation, what you already had engineers? And the answer is yes, we are actually learning something new. These are independent features. And how are you going to test it? You're going to look at the scores that are coming out of your RNN. So these are your scores. And then you're going to look at the scores that are coming out of your statistical machine translation. If they were the same thing, you would see a line here. They would be heavily correlated, but you don't see any particular correlation in these scores. So yes, you're actually adding some new information. You're looking at the same problem through the lens of two different approaches. One is classical and one is a neural network approach. Okay, if you do that, how much gain do you obtain over the baseline? The baseline is most, you can find the code here. It's on GitHub, you can download it and play around with it. On the development set and on the test set, this is how much improvement you're gonna get by adding the features from your neural network. And basically you're increasing your blue score. And in terms of qualitative performance, If you look at it qualitatively, I think this is pretty clear here. There are some random stuff here. RC, there are some question marks there, so it doesn't know what those words are. Once you add the RNN encoder decoder, most of those random stuff are going to go away. And these translations actually make more sense. That's for long, frequent source phrases. You can have some rare source phrases, and still, qualitatively, your predictions or your language is doing a better job, your translator. There is one more thing. You can actually take a look at these embeddings that you're learning out of this process. We know about word embeddings. You can actually learn word embeddings through translation from one language to the next one. If you look at word vectors and you visualize them using something like PCA or TSNE, etc., you can see that these words are clustering together. And let's focus on this blue part because this figure is a little bit cluttered. If you look at this part and you zoom in, you see that most of the countries are sitting next to each other. France, China, Russia, English, French, Germany, Ontario, Iraq, British. So these have to do something with country. Okay, you can actually learn word embeddings out of translation. Any questions before I move to the next topic? The question is, why is G learned? Why are you decomposing G? Aren't you going to end up with the same number of parameters, or aren't they mathematically equivalent? You're doing it for computational reasons. And no, they are not going to end up being equivalent. You're going to have far less parameters if you decompose that way. And computationally speaking, you're going to have for loops that are smaller. So you're doing iterations less. So computationally speaking and memory-wise, this is more efficient. This is like doing SVD, singular value decomposition, but now you're learning them. So it's more efficient computationally. So we learned two ways to get help from neural networks to improve the quality of our translation systems. One of them was, okay, let your baseline do the translation for you. It's going to give you 1,000 good translations and use a neural network to rescore it. The other one is to add your neural network scores as features to your statistical machine translation. So for this, you had to change your algorithm a little bit. So you're changing your statistical machine translation a little bit. You're adding some features and you learn these parameters. Is everything clear?
The WN in that formula you were just highlighting in the middle column, the WNs are weights?
Yes. So if you had a statistical machine translation framework, and this is actually what Moses is doing, you spend a lot of time featureizing, but once you do your feature or your featureization, the rest of it is a linear regression.
Okay.
These are linear ways that you're going to learn.
And the scores that are coming out of the encoder decoder, you can also just think of them as like vector embeddings.
Yes, so these are going to be vectors actually.
Okay.
And these are going to have the size of your vocabulary. These probabilities, they're going to have the size of your vocabulary. So you're going to add a lot of other features.
And so it's a vector the size of your vocabulary that has like a high weight at certain words that are important.
Yes, and that's going to depend on the input data that goes in. So it's going to depend on E and F.
Okay.
Here, X is going to be E and F is going to be Y.
Got it.
And you're going to add that vector as a bunch of other features to your feature dictionary.
Got it. And the other question I had was if the probability of E was in the denominator up above with the Bayes rule, wouldn't this be minus log?
Yes, so you're taking the negative here.
Okay, so Z is like the negative probability.
Yes. And in the end, it doesn't matter. It's just a constant in your objective function. What you care about are these W's. When you're going to maximize this log of the translation, it doesn't depend on Z.
Yeah.
It depends on W's. So you're maximizing with respect to W's.
Is this linear combination is a model for the P of E given F times the probability of F?
Yes, so this is a model for the joint distribution.
Yeah.
It's kind of P of E, comma F. And this is the product of these two.
Yeah, perfect. Thank you.
Okay, any other questions?